share your document.
Oh, cancel. Okay, I'll try this one at the top. Okay, so if there are no specific questions about linear solvers, then let's talk a little bit about nonlinear solvers. So the problem I'm going to use is, again, a little bit close to the pilot problem, but much, much better understood. And this is what's called the driven cavity problem. So you have a bunch of fluid in a box, and you hit the top of the box with the hammer. And this is thus the Stokes problem. In PETSI, it's formulated in this velocity vorticity form. I think you could probably do that for elasticity, but it would look really weird. But this kind of Stokes problem is somewhat close to what we get in pilot. We also have a saddle point problem. We also have an elliptic operator in the 0-0 block. But the connection between the elliptic part, the elasticity, and the auxiliary part, here it is fault tractions instead of pressure. The connection is algebraic in some sense, this requirement of a fault slip, rather than being differential like the incompressibility constraint is in Stokes. And in fact, that fault slip requirement is a little bit fake. It's a little bit artificial, right? It's just the first thing you might do. When Brad is showing the more sophisticated formulations, we impose some kind of a friction law to connect the tractions and the bulk elasticity. And when you do that, then it's not the same algebraic connection either. Now it's some kind of connection mediated by an intermediate ordinary differential equation or a differential, some sort of thing like that. And then our problem becomes, and a lot of times there's inequalities involved in that definition, and then our problem ceases even to be a PDE. It becomes a variational inequality. So the PETSI is the pilot is a pretty advanced formulation. So what I want to do is first talk about a simpler formulation that's driven cavity, and I hope to shed some light on what we might be able to do for the more sophisticated solves in pilot. So hopefully this kind of a Stokes problem is somewhat familiar to people. This Grashof number, I'm going to keep the Prandtl number at 1, so Grashof number is really the Rayleigh number in that situation. So you can just think of it as the Rayleigh number. What's the vigor of convection? I'm going to do this on a regular grid. The reason is it's really easy for me to show off multi-grid results on a regular grid. In theory, all this can be done on an irregular or unstructured grid, but we need ways to do coarsening. So, research project. So here, I'm just going to do a simple solve. You can see that I have SNES monitor on, so it prints the residuals. The monitor short truncates the number of digits you use in the residuals. That's almost always what I want for the printout. And then I print the converged reason. And so what you can see is this converges just fine. It takes a few Newton iterates to get into the region of convergence, but then it zooms right down. So everyone is happy. If we raise the Rayleigh number, what that means is we are driving the system harder, and we get more vigorous convection, and we're edging towards turbulence. Turbulence doesn't set in really till maybe a million to 10 million. But as you get closer, the systems become harder to solve. This does not show it that it looks any harder, so maybe you don't believe me, but if you increase just one more, and I just want to emphasize, if you follow this link, it'll show you the code in PETSI, and in your pilot installation, you can go into PETSI and run this if you do the source installation instead of just the binary. You can do all these runs yourself. Even with the binary, you can download the source code from this link and build it using the PETSI parts of the binary and run this yourself. By the time you get to about 100,000, the nonlinear solve starts really to break. Now, the first thing that breaks is that the linear solves become much harder. And this you see also in the fault friction problem. The linear solves become quite hard. And so what we can do, though, is it's small enough, we can put PC type LU, which should always be your first response, and then we don't fail to solve the linear problem, but unfortunately, the solution to the linear problem fails to do us any good. So you can see that we just stagnate with Newton here, and we're not solving the problem. Now, people have developed many different ways to cope with this. They have said, well, let's do coarser solutions and then try and use that as an initial guess. This is called grid sequencing or one-way multigrid. Unfortunately, for this problem, that doesn't work. You can do continuation, where you say, let's use the solution, let's use the solution for Rayleigh number 10,000 and start off Rayleigh number 100,000 on it. Well, that doesn't work either, because the solutions for these things in this parameter are really different. Continuation does work, does tend to work when you're doing things like changing the elastic coefficients, changing viscosities, that type of thing. It does work pretty well. But for this situation, changing the Rayleigh number, it's no good at all, which is why I chose the problem. There's this taxonomy of things that might happen, and I just put this slide up here because if you see this happening in your pilot code, you might go down this kind of checklist, although number one, the Jacobian is wrong, will never happen to you because there are no bugs in pilot. The linear system might not be solved accurately enough, so this could definitely happen to you. So I would go back to not using PC type LU, but the PC field split with the full Schur factorization. And this is a very helpful option, KSP monitor true residual. That can be used to inspect the performance of your preconditioners. Sometimes preconditioners can lead you astray. Some preconditioners, particularly algebraic multigrid, are prone to developing singularities. And this will show you whether the precondition residual can be very low, but the true residual can be high, and thus you get no convergence. So it's good to check that. It's possible to get a singular Jacobian. As I said, you can make problem definitions where this happens. So if this and you'll know if it's singular if your the thing you try above, the LU, fails. And if that fails, then you have a singularity and you have to try to deal with that, perhaps by giving a null space to the preconditioner. Or at the end of the day, the nonlinearity can just be really strong. And this is what is happening in this problem. When I got to Argonne about 12 years ago, this was the state of the art. What I've just shown you is the state of the art. And when it failed, we just didn't know what to do. And this was really frustrating for solver people. And you got a whole bunch of crappy answers. If you've ever heard of these Newton globalization strategies, this is not, see, the thing is, people, if they have a hammer, they want to hit something with it. A globalization strategy was really designed to get around the problem that occurs when you have a whole lot of pretty valid answers. So you have a lot of what's called local minima. So that's actually getting a solution to the problem and saying, well, it wasn't exactly the solution I wanted. I wanted another one that's a little bit better that's over there. And this happens in a lot of optimization problems where you have combinations of the inputs that produce pretty good answers. And you just want the one over there that's a little bit better and it's hard to get to it. This is not what's happening here. What's happening here is the dang thing just won't be solved. And so people who are using these globalization strategies for that were just messing around. And I think that's what the case is for these trust region methods. I think that's just BS, to be honest. Sequencing does help a little bit, but in this case, it fails. You can drive the Rayleigh number high enough to cause it to fail. And it's the same with continuation. So it was just really tough. When we got here, we just didn't know what to do. And most practitioners just accepted that and redefined their problems. Took out the strong linearity or simplified somehow so you didn't come up against this wall. But in the last several years, progress has been made in nonlinear preconditioning. So what do I mean? For a linear problem, you can take something like a Krylov solver, and you can do this subsolver on each iterate, as I said, Richardson. So Richardson is the simplest subsolver. It's just, it's basically what's usually called steepest descent. It's made up by this guy, Louis Fry Richardson. Now, in a nonlinear regime, what you might think of doing is a nonlinear GM-res iterate where there's a subsolve on every iteration, and here you can use this nonlinear version of Richardson, which is the simplest thing you can do. And this is our inspiration for the nonlinear preconditioning in PETSI, and these PETSI options actually work exactly this way. So I'm not going to talk about this slide. So let's go back to the problem that was failing, and I want to show you how you might build a stronger nonlinear solver the same way you would build a stronger linear solver. So we're going to go back to the situation where it's not converging. Here I'm going to just take the Grashof number down a little to 50,000 instead of 100,000. Because you can gradually see the solver converge again. I can take it back up after we get the really strong stuff. So we're here in this situation, and nothing's converging. Now, instead of Newton here, we can replace that with what's called FAS. This is just nonlinear multigrid. So remember I said that we could try grid sequencing. Well, this is basically the strongest form of grid sequencing. This is nonlinear multigrid. And we'll use a bunch of levels, and on each level we'll use what's called a Gauss-Seidel solver. This is exactly how linear multigrid works. You use a Gauss-Seidel or an SOR solver, and we try this, and it looks like it's doing okay, and then it fails. So what's this failure? Diverged inner. Well, I didn't know either, honestly. So I was like, oh, because I didn't write the nonlinear multigrid. And I said, that's not the greatest explanation. So what do I do? Well, I can get some more information about what's happening. So I add this, tell me what's happening on the course level. And so because I figured that's the inner solve that's failing. And what you can see is these course levels, sometimes they converge, sometimes they diverge. But the thing that went haywire was not kind of the solve itself, but the line search. This diverged line search causes this diverged inner error. And it's hard to see unless you turn on this inner monitoring, right? But you can always do that. So we try to have a simple, obvious path for increasing the amount of information that you get back about all the PETSI solvers. And hopefully that's how it works. Oh, crap. What? Okay. So now we can turn off the line search itself, and what we see is we turn off the line search. It no longer fails, and we can see convergence of the course solve. But unfortunately, that convergence of the course solve is not strong enough to cause the whole problem to converge. So this is really what I've said before, is that grid sequencing doesn't work because course solutions, even if they're accurate, are not good enough to get solutions to the whole problem. So that's a real problem for us here. This Gauss-Seidel iteration is just not converging for us. So what do? So now what we have is the option is to use a nonlinear preconditioner. Now, unfortunately, it's a little hard to see which is the solver and which is the preconditioner in the nonlinear sense. What we're going to say here is that the outer solver is a simple Richardson iteration, which is just apply the operator once, basically. That's it. So we're going to do one iterate of that, and then for each of these, the preconditioner will be this nonlinear multigrid that we used before. So we add NPC to all these nonlinear multigrid, and the outer solver is this incredibly simple Richardson iteration. But adding that just simple one-step correction, you can think of Richardson actually also as iterative refinement. And just adding one step of this iterative refinement on the outside, we can go from no convergence to convergence. What happened? Oh. So that, to me, this is the single greatest thing I have seen for nonlinear stuff, in a decade. This neat little non-convergence to convergence from this one option. If you solve a lot of nonlinear stuff, I think this will be amazing. And the thing was that this had been shown in isolated cases before, but always for specific problems with specific solvers and never phrased in this general way of having a preconditioner. Now, we not only can do that, but we can allow you the same kind of freedom that you have in the linear problem. So maybe you want to say, well, Richardson's pretty cruddy. What if we use nonlinear GMRes instead of Richardson? Well, then the number of iterates goes from 45 to 29. Now, I want to be clear. So in a linear problem, if you go from 45 iterates to 29, that is great. But that's doing about 16 less matrix multiplies. In a nonlinear problem, if you go from 45 to 29, each of the iterates you save is a whole linear solve, and it probably has 60 or 70 iterations. So it's an enormous amount of time that you save. So as you go up the tree, the savings become more and more powerful here. And in fact, we can really hit it with the hammer here. Instead of Gauss-Seidel, this thing, we can decide, instead of Gauss-Seidel, we can decide to use a very strong level solver, a full Newton with all of the iterates on each level, and you can converge the whole problem then in the same 5 iterates that you were used to for very small Rayleigh number. So we have all the tools that you expect for linear solvers now in the nonlinear regime, but it is very, very new. So it only happened in this latest 3.4 Petri release. I don't know anyone that uses them except me. And so I'm trying to encourage people to investigate and play with this because I think it's very, very powerful, and the savings that you're contemplating can be orders of magnitude bigger than the linear savings. So I really think about it that way, when you're talking about optimizing codes. I'm not going to talk about fault friction. Brad talked about fault friction already. However, it does have all these nonlinear issues, and we're working on them. So if it is failing for you, please do contact CIG Short, and we'll try to work through what is going on.